Welcome friends. Today we'll discuss about or rather simulate pendulum system equations of motion in Simulink. If you're wondering which MATLAB version I am using 2024B. So you also will be getting an online version where you can practice in MATLAB and Simulink. Now let us proceed with today's topic, that is simulating pendulum motion in Simulink. So we'll use different methodologies. First, let me draw the figure here. This is a bob of mass m acted upon by the gravity force. Here we have mg sine theta in this direction. So this is, I am considering this as positive theta. This damping will be in the opposite direction, c theta dot, and this is the torque. So we know that the equations of motion for a pendulum system shown in figure can be written as theta double dot, that is second order differential equation, equals to 1 upon ml square into t minus g upon L sine theta minus c upon ml square to theta dot. So I am continuing with my numbering system. This is equation number 30. So here theta is representing angular position of the pendulum. Theta dot is angular velocity of pendulum. Theta double dot is angular acceleration of pendulum. T represents the torque or the input to the system. M is mass of the pendulum bob. L, this is the length L. L is length of pendulum. That is from pivot to the center of mass of bob, and we are left with C, that is the damping coefficient. Which is nothing but the resistive forces against motion. So again, I am not going how this equation has arrived. That is not the intent of this course. So we'll simulate this pendulum motion using different methodologies. First, we'll try with MATLAB function. So before that, we need to convert this second order system, second order equation to two first order equations. Like we did in the last lecture, let us follow the same procedure. Let x1 equals to theta and x2 equals to theta dot. Likewise, differentiating above equation with respect to time yields x1 dot equals to theta dot. Theta dot is nothing but x2 and x2 dot equals to theta double dot, which can be represented by equation 13, 1 by ml square into t minus g by l into sine of theta. Theta is nothing but x1, again transforming the variables into nu, minus c by ml square into theta dot. Now what is theta dot? Theta dot is x2. Now this equation, let me take it as equation number 14. Now for simplicity, let us consider the values. For simulation we need values. Consider g as 9.81 meters per second square, l as 1 meters, c equals to 0.5 Newton meter per radians per second, mass is 1 kg, torque I'll consider it as 2 Newton meters. Now let us jump to Simulink. Now I have already modeled here and plotted the position and velocity using different methodologies. What we'll do is we'll reproduce the results using this Simulink block. So I'll start from the scratch. I'll take it as new file, or you can go to Simulink either by clicking writing here, click on the create model and save this model in your working directory. I am naming it as Simu test. So now let us use the first methodology, that is the MATLAB function. I'll start typing here in my keyboard MATLAB function. Here you can see a MATLAB function is appearing here. Just click on this function and here we will write what is the input and what is the output that is required to run this MATLAB block. So it appears automatically here. U is the input and Y is the output. Now here we have two outputs, x1 and x2. This is the MATLAB function that I was talking about. Let me just copy this code here. So here input is the x vector, that is x1 and x2, and t is the torque, and g 9.81, L1, C 0.5, M is 1. So here, since x is a vector, we need to write what is the first element of x. I am denoting it as x1. x1 is x of 1, x2 is x of 2. And these are the equations: x1 dot equals to x2, x2 dot equals to t by ml square. The same equation that I have written here: x1 dot equals to x2, x2 dot equals to 1 by ml square t minus g by l sine of x1 minus c by ml square into x2. This is equation number 14. And what is the output that I have written here? Dot equals to x1 dot and x2 dot. Now we actually need to integrate this equation. We simply write integrate. We get a block here, integrator. It is denoted by 1 upon s, which is again fed back in this manner, and it needs some initial conditions. Let me write the initial conditions as position and velocity. It is, I'm assuming it starts from 0 degrees. So I'll write here 0. Remember, MATLAB always considers the values in radians. So if I have written in degrees, convert into radians, into pi by 180, and the velocity is 0. Transport it. We have to write in a column wise. So this is the initial values. These are the initial values. And we need some torque here. Let me consider the simplest of the input function is step function. We had written a code for writing a step function in MATLAB. So in Simulink, we already have a block, that is step block. Now consider an torque of 2 Newton meters, which is applied at 5 seconds. Apply and OK. Let me run this for maybe 30 seconds. I am saving, and let me see if I am getting any, if it is indeed running or not. Yes, it is actually running. Now to plot these responses, now this here x is a vector. We need to see the plots for position and velocity. We actually will demux it. So it will demux into 2 vectors. I am right clicking and dragging just for creating a branch. So the first vector is actually a position, and the second is velocity. To see that, we have to write here scope, and again to copy this, either you can do Control C, Control V, or right click this block and simply drag it. Now if I double click this, so nothing is shown here because it is already run, and I have used this scope block later on. I simply need to run this. So here we have position or angular position, and this is the velocity. So here we observe there is sort of sluggish response here. What we'll do is we'll increase its frequency. So here we can see after 5 seconds, because of the control torque 2 Newton per meter, so there is an angular displacement here of about 0.2, and this is again in radians. First we'll convert it to degrees. You'll write here radians to degree. That will be converting into degrees. Again right clicking this option and dragging it. As simple as that. So now actually we'll get the response in degrees. All right. Now let us make this response a little bit smoother. For that, you have to go to modeling, model settings, model settings. You'll write here maybe fixed step solver. Let us use Runge-Kutta method and give the frequency as 100 hertz, 0.01. Apply. Okay. Now I'm saving the file, and now let us run this code. It is ready. Yet we can see here bottom left, and if you double click this, now we have a smoother response for angular position and as well as velocity. We can go ahead with the print display to figure, and we get further options to see these data points. We can easily pan it out. So you are encouraged to explore these options, and there is another option to actually bring these variables directly to the workspace. So for that, let me go to the MATLAB here. Let me create another file. Let me copy paste this code here, and see here again, actually we have to define the variables g equals to 9.81, L, C, and so on and so forth. If you go to this MATLAB function, this is a function. Actually, if you have ever worked in function file in MATLAB, we know that these variables will remain within this function file. So these variables will not come out. Only the output variable will be dot. Other than that, everything remains in this function. Hence, if you are using a MATLAB, or if we are trying to call a Simulink from MATLAB, we need to redefine these variables. Now TF is the time I am considering as 30 seconds. So let us go here. Let me write here stop time instead of 30. TF dt is 0.01. Again go to modeling. Instead of directly writing 0.01, I'll write here dt. Apply. OK. And x naught, initial condition is 0 and 0, 0. Let me write here x naught in the place of integrator. Apply. OK. And the name of the file I have written is simu_test. Let me write here simu_test. Make sure both the files are in the same folder. So I am saving it. simu_test_MATLAB. Now what it will do is, after coming to this line number 10, it will run this. It will look for the file name as simu_test, and it will run that. So let us test it. So it was successful. T out is 300 by 1. But if you see this workspace, we haven't got the vectors x1 and x2. So to do that, we need to send these variables to the workspace. We again go back to our Simulink model and type to workspace. And we go back to modeling settings. So this output will not give me a vector. So we need a vector of x1 and x2. So to do that, just uncheck this box, single simulation output, and let me rename it as SimX. All right. Now we again need to mux these signals. So the opposite of demux, it is mux, MUX. So I'll branch out this first signal here. I am right clicking the signal and then dragging and dropping here, and this is the output. Now let me run the code directly from MATLAB and observe in the workspace. So now it has run successfully. Now we have simx variable, but it is in this form. We cannot directly extract from here. So what we need to do is we write a simple code for extracting in x1 and x2 variables, and the syntax for that is simx dot data all the rows and the one column, first column, and the second column all the rows. So now let me run this code. Figure 1, that is subplot 2 comma 1 comma 1, 2 rows 1 column, that is first figure. Similarly 2 rows 1 column, second figure. I have multiplied this by 180 by pi from radians to degrees. Similarly radians to degrees. Rest of the things remain same. Here GCA represents get the current axis for defining the font size as 14 and font weight as bold, so that it is clearly visible. Now let me run this file. Before that, let me close if there is any scope is opened. Yeah. All right. So this is the one that I am getting the response here. Now let me check whether the similar response is observed here or no. So this is the position, and let me just bring that. Yeah. So it is going up of about 12 degrees, the angular position, and similarly angular velocity is going to 0, that we can see here as well. So both responses are similar. So there are different methodologies. You can get the, if you are interested to find angular position or velocity, you can use either of the methodologies. All right. Now let us keep this final value as 0. Let us see the response. Let me close this. Go to the MATLAB again and run the file. See now. So now there is no response because there is no input. That is quite obvious, but still many times students get confused if that why do we have response in position and velocity, why it is not going to 0. Let me close this again. I am running the file. Yes. So here we have two responses. Here we have angular position which is settling around 11.8 degrees. All right. So here the response will not be, it will not be 0 because we have a constant input which is acting upon the pendulum. That is why we have some response. Now let us quickly obtain this response, similar response, by another method. Remember, for mass spring damper system we have drawn a block diagram. So let us use that block diagram here. Here we have to integrate two times. So I am representing this as integrator. One more integrator. So here the input signal is theta dot, theta double dot. This is theta dot, and this is theta. And here, for theta double dot, we have three variables: t by ml square minus g by l sin x1 minus c by ml square x2. So here let me write this as plus, that will be for torque. This is minus, since both are minus here. And consider this as again c by ml square. which is theta dot c by ml square is multiplied by theta dot, c by ml square is multiplied by theta dot is nothing but x2. All right, plug this here. Then we have g by L, and this is multiplied by sine. What it will do is it will sine off this angle multiplied by g by L, and then this is subtracted from here. Then here we have 1 by ml square, which is the gain here, which goes here, and this is the torque T. Now let us plot this, let us draw this block diagram directly in Simulink. All right, I'm right clicking this integrator. We need two integrators. Let this be 0, there is no acceleration. This remains same, x naught. I'm writing here some block. We had three variables. Let me represent it by rectangle, which is plus minus minus. So this is nothing but theta dot, theta double dot, theta dot, and this is theta. So here we have to write gain. We need to flip this model, gain, format, flip log, or control plus I. Next time I will be using control I. Here I'll write C divided by ml square m into L square. This is element wise multiplication. And then sine of theta, control I, sorry, G by L, this goes here and this goes here. And here we have another gain, 1 by ml square by ml square, and the same torque I will provide it here. Now let us directly plot scope. This is theta. We'll convert it to degrees. Similarly, theta dot, that is velocity, we'll convert that it's also to degrees. All right, I think we are more or less done. Let us run this code. So here we have again position, angular position and velocity. Let me go back to Simulink model. Let us see, are we getting similar response? And this is the angular position and this is the angular velocity. All right. Okay. Yeah, so we get almost similar response with this block diagram methodology for angular position and as well as angular velocity, which is going towards this is 0. So you can use various methodologies to find or to plot the response for y with respect to time. So in the next class, we'll be using a state space model and another method in Simulink simulation. All right. Thank you.